what am I going to talk about today? We're talking about source adaptation. So first the why, then the how. The VSF board approved TR064 Part 1 back in November. So we're going to describe that. And then we're going to show some implementation results. And we have it running downstairs as well. So if you guys went to the VSF fall meeting in New York, some of these are the same slides, so you have my permission to sleep for the next 10 or 15 slides. Otherwise, just pay attention, right? Okay. Why RIST? RIST is, the basic function of RIST is to recover packet loss. It's the most fundamental function of RIST. However, if the network capacity falls down below the stream rate, there's no retransmission that's going to work, right? You can't cram a 5 meg stream on a 4 meg pipe. That's it. So you got to solve that at the source. You either reduce the stream bit rate, or if you have multiple links, you rebalance or reroute the stream. So that's got to happen for reliability. So fine, this has been happening forever. Lots of companies have that. Why do this in RIST? Source adaptation is a very important feature in some applications. Cell bonding is the typical one. And in many cases, you can't have reliable transmission without source adaptation. We call it reliable internet stream transport. It's got to be reliable. So you got to have that. If we add this to RIST, there's multiple advantages. There's already a framework in RIST to send between sender and receiver to report information. And obviously, why we do this in the context of VSF and RIST, multi-vendor interoperability, so you can mix and match. So the same stuff that we've been saying since 2018. All right, let me show you where this fits in the RIST technical recommendations. We had simple profile for low latency delivery. Main profile added the tunneling security. Advanced profile, the main thing is use of RIST as transport for other protocols. Then TR064 is the RIST ancillary features, and this is TR064 Part 1, which was approved November 2022. There's another one, which is WireGuard, was approved in January 23, and we are working on other parts. So, where does it fit? You have an encoder that may go through a RIST gateway, that's the sender, that transmits through the network, and then as a receiver. What TR064 define is what we call link quality messages from the receiver to the sender. So tell me, how are you receiving? And the RIST AG decided not to specify the blue line, the control protocol between the RIST between a theoretical RIST gateway and an encoder, because this would be legacy encoders, and if you're going to upgrade the legacy encoder, might as well put the whole protocol in. So we're not touching that. So what is and isn't in TR061 Part 1? What is? Method to report statistics, support for global and per link statistics. I will talk about that later. What isn't is the encoder protocol, encoder control protocol. You build it into the encoder if you have to. And an algorithm, the actual algorithm to decide how to increase or decrease the source bit rate or modify the routing, we left that out. There's a simple example on the TR, but the vendors can innovate on that. And there is some sort of an IPR minefield on that, so just be careful there. This is the link quality message. And I know it takes people to sleep when we talk about protocol fields and everything, but I got to do this, so I apologize in advance. It's not a big message. It's 11 parameters at 32 bits each, so it's just 44 bits. And how we encapsulate that in RIST depends on the profile. So I'm going to tell you what the parameters are, and then I'll show you how to encapsulate it. So first parameter is a sequence number, so you can see if you lost messages and if you have duplicates. And consecutive messages correspond to consecutive intervals. There's no retransmission mechanism because this is information that needs to be acted upon immediately. You lost one, too bad. Reporting period, that's one important thing. The reporting period can be dynamically adjusted. So we report that. But if the network is changing very rapidly, the receiver can send the messages faster. We put the NAC window size there just because. What else? SAS packets received, the important parameter, includes everything, including FAC, actually, and control messages. Original packets lost, so this is packet loss prior to retransmission. Retransmissions received, recovered packets, and unrecovered packets. So if you couldn't recover, that's a good count. Late packets, packets that are received too late, but to be used outside the window. This is also an informational item. You know that your NAC window is not enough, or there's too much delay. We have measured data bandwidth, so you have an idea what the bandwidth is. It's also more informational, and measure retransmission bandwidth. This is important to put because you can't necessarily derive that from packet counts, since now packet deletion can be in place. All right, so essentially not all packets are of the same size. All right, now that you are all experts in that message, let me show you how we encapsulate that. And we'll start with simple profile. Simple profile requires RTCP. And you need to send receiver reports periodically to keep firewall state. So we just use RFC 3550 to add profile-specific extensions. So it's what Mr. Ackerman says, the Lego approach. Just use what's there and tweak it. So we just adopted that, which is backward compatible with any RTP devices. So a compliant RTP device will just ignore it. So it looks like this. You have a receiver report. The white stuff is what is in RFC 3550. We took a quick look at that. We thought about it about 30 seconds and said, that isn't useful. So we define a new message, which comes after that, what's in green. And you can also use the empty RR as well. Okay, RIST main profile encapsulation. Well, main profile is a tunnel, so there's no special encapsulation for main profile, so it just carries. So there's nothing to do in main profile, all right? RIST advanced profile encapsulation. Now we need to do something different, because advanced profile uses RTP but not RTCP. So what we define for simple profile cannot be used in advanced profile. So we defined something different. Also, it was recognized that if you are in multi-link mode, it would be nice or interesting to have per-link statistics. We cannot do that in simple profile, but we decide to do that in advanced profile because advanced profile's got control messages. So we just went and defined new control messages. We left a lot of codes in there to define new stuff. So this is the list of control messages in advanced profile, and we created a couple more. One for global and one for link specific. So a note for multi-link operation, you may have multiple links and you may be using that or bonding or replication, but seamless switching. So we have these rules. All the streams must send identical copies of the global reports on all links. That's what happens in simple profile. You may optionally send a link specific quality. So you don't have to implement link specific, but if you do, you send it after. And simple profile is only global reports. So let's talk about the difference between global and link specific. Global is everything combined, transmitted over all links. And it's important that the packets received, retransmitted packets, or count late packets includes all the duplicates. So if you are doing seamless switching, you're going to see twice the bandwidth, twice the number of packets there, because it includes duplicates. Same thing with the bandwidth, right? You will see, if you're doing seamless switching, you'll see twice the bandwidth in the report. Link specific, it's computed only for the packets received in the link, but not all parameters can be link specific. lost and recovered packets, you have no knowledge of where the packet was sent, so you don't know. So then you use the global version. So that's a little table which I copied from the TR, which is available for free, and shows you which ones are link-specific and which one are global. So even if you're sending a link-specific message, the lost and unrecovered packets are going to be the global values. All right, I said that the TR does not include the encoder adaptation, but it includes an example. That's an informative section. What we did in the TR is just to put the mechanism to convey the information. All right? So it's an informative. So, for example, you may implement it this way. If your number of unrecovered packets is non-zero, all right, you couldn't recover some packet, or the number of the lost packets is higher than a certain level, the encoder will decrease the bit rate. So decreasing is easy. How do you increase? You may implement as if the number of unrecovered is 0 and lost packets is less than a certain level, you can increase. Because I say, okay, I'm working well, this is working for me, maybe I'll try increasing the bit rate. You can use the information any way you want. I think that's the nice thing about the way we did this TR. The algorithm's up to you, so we can innovate, and everybody still works with everybody. And here's a source adaptation as example, thanks to my friend Adi, who did that picture and prepared the example. Let's say that you have a sender with 3 links that split 30, 30, and 40%. So 30, 30, and 40%. My animation works. Not as good as his, but it still works, right? Let's say that link A shows a 10% increase in packet loss. Then you adjust to 20, 35, and 45. So that's a source adaptation example. You should do source adaptation first before you do bitrate change, because it's more powerful if you have multiple links. If you have a single link, you're stuck. All right. This was a quick overview of the TR-06 for part 1. It's out on the VSF website. You can download it, you can read it, and you can, I don't know, read it. I was going to say something I shouldn't. All right. So we have, Cobalt has an implementation of TR-06 for part 1 in our RIST-capable encoder-decoder pair. It's on demo downstairs. So here's what we did. We did a simple profile with global reports only, and we did encoder bitrate adjustment. We have a fixed half-a-second link quality report, and the encoder will immediately adjust the bitrate. It's the ASIC we use. One important thing for compliance, many professional IRDs want a CBR stream, right? So you can't really change the rate. What you got to do is get rid of the null packet. So you decrease the video PID rate, so the encoder will give you more null packets, and then you use TR-06 to null packet deletion, which is you remove the null packets and put flags where they should be, and then the other side can put them back, and you use that. So you can, on the other side, reproduce a compliant CBR transport stream at the original rate by recreating those null packets. So the algorithm we used in the implementation is a variation on the simple algorithm in the TR. All right, first thing is lab testing. So we have a custom Windows network simulator which can do bitrate limit. So you check a box and then immediately puts a bitrate limit using a leaky bucket. So in this test, the video was sent to maximum of 10, minimum of 3, giving me 11 megabits transport rate, and I set it for 8 megabits per second. So when I check that box, it goes down to 8 megabits per second immediately. So that's a test. That program, that Windows program, is available for the asking. So if you want to play with it, just find me after this, and I'll give you a copy. We just give it away for free, as is. But it's Windows only. And yeah, you all can say, oh yeah, you can use that, do that with TC in Linux. Yes, you can, but this is like nicer for demos. All right, here's a result. So in the Y, you have the encoder bit rate, and the X, the time in seconds. So I turn on the encoder right there. Then I turn on the bit rate limit, and packets start getting lost because I'm pushing 11 on an 8 meg pipe. So the encoder aggressively drops the bit rate to all the way down to 4 until it clears all the problems, and then it starts raising again slowly and goes into some steady state where it raises, starts to see packet loss, and then goes down. Raises, and it will go there forever. And that is within the rate limit and with no packet loss. When I turn on the simulator, then there is uncorrected packet loss. But then operation within the rate limit, it can work without any packet loss. And then I turned off the bitrate limit, and it went back to the 10, which was what it could do, because there is no limit anymore. So that's one test result. And you see there was a big jump to 4, right? So RIST has a feature of limiting the retransmission rate. So let's see how it works with that. So I turn on the encoder. Now I limited the retransmission rate, and it didn't drop as much. So you can tweak that on your sender too. If this is obviously an artificial thing where the bit rate is immediately limited in a step function, but depending on how your sender is configured, using the same features that have been in Simple Profile since 2018, we can have better performance. So in this case, I just turn it on and turn it off and let it go back to maximum. So this is all lab testing. We're testing in the lab. The encoder is right next to the decoder with the Windows machine in the middle, constraining the bandwidth. What about the internet? Well, Cobalt's got offices in California and Illinois, our headquarters. So I tried this from Santa Clara to Champaign. And downstairs, the demo is Santa Clara to here, same encoder. I set it from maximum of 8 and minimum of 2.4. And this link has a 75 millisecond RTT measured by the RIST RTT message. It's been there in Simple Profile since 2018 or 2019. Okay, and I left it run for 64 hours. It was over the weekend, so people don't get upset with me. But actually, we have plenty of bandwidth in Champaign, so they wouldn't even know. There's a cable modem in Santa Clara. There's a Comcast cable modem, and we have some other service in Champaign, different ISP. So this is the beginning of the test. You see here, I captured the moment where I turn on the encoder turns on, goes to maximum bit rate, and says, whoops, I can't do that. And you can see there that it goes up and down, up and down, up and down. This is the first 45 minutes of the test. Up and down, up and down, up and down. And now the whole 64 hours, it was able to go to the top a few times, and you see there Monday morning probably where the network got really congested, so it went all the way down to the rail. And then people stop. I mean, this is my guess. I don't know. I don't have visibility on what's happening there. But this is a full test, full 64-hour test using this stuff. And I would say we had a problem with shipping, and I had a new set of equipment sent here. I had this thing running in my hotel room on Saturday with the PC as a bridge to the hotel Wi-Fi, and it was working fine. It's the same thing that's downstairs now. You'll see, I encourage you to come see in the demo. So what I have learned so far, there's more things to learn, and there are more things to learn about multi-link. But you saw that best results are obtained when the sender is aggressive in reducing the bit rate and slow to increase it. That's not the first thing I did. But that, if you aggressively increase, you can't recover as fast. So this is just my experience. Again, you can innovate. I'm just laughing because it's done this way before I did. If the sender is transmitting to multiple destinations, it must keep state on a per SSRC basis to make decisions based on worst case scenario. So you need to be looking at that. If you're doing seamless switching, the protocol itself will combine the results. So this is what I got. This is implementation of TRL6 for part 1, and again, it's on demo downstairs as part of the RIST demos. Any questions?
We are recording these sessions, so if anybody has any questions, come on up. Doesn't look like it.
I left them speechless. So
I know you did. They're stunned. Either that or they're just kind of warming up.
Yeah,
Ciro, thank you very much. We appreciate it.
Welcome.